telling us how you started working in the machine learning space and your path to the present? I know you're not like a hardcore computer science person from training, so how did you get into this? Yeah.
Yeah, so I'm a chemical biologist by training. So um, I started, and specifically an antibacterial chemical biologist. So I started getting interested in novel antibiotic discovery from the perspective of like the wet lab, right? So this is like pure experimental work. When I
Yeah.
was an undergraduate student, that was back in like 2010, I think I started doing antibiotics research.
Yeah.
And again, this was like, from my undergrad and then through my PhD, it was lots of like high throughput chemical screening, um,
Hmm.
in vitro genetic and biochemical, small molecule validation, in vivo work, this type of stuff, right? Um, and then when I made the transition from my PhD into my postdoc in Jim Collins' lab, right? Um, his lab has, they do a bunch of, systems biology type stuff. More computational approaches are commonly used. So I was just
Hmm.
kind of in this environment that, you know, promoted the development of that skill set, I would say.
Yeah.
And then what happened to get specifically into machine learning is uh, Jim Collins introduced me to Regina Barzilai. Regina
Hmm.
Barzilai is an artificial intelligence expert professor at MIT. And the year before we started working on this project, so she would have published a paper, I believe it was 2018 or 2019, but her lab developed this message passing neural network architecture for physicochemical property prediction, right? Not
Okay.
biological property prediction. So, you know, Collins, myself, Barzilai, a few others got in a room and we were trying to figure out, okay, how can we leverage each other's expertise in order to
Hmm.
bridge this gap between antimicrobial drug discovery and machine learning molecular property prediction specifically, right?
Uh-huh.
And so, right at that time, I had just sort of introduced high throughput screening to Jim's lab, right? We
Yeah.
just bought our first chemical library, started messing around with that. So it was very clear. It's like I had this small, it was only 2,500 molecules, training data set. We can
Hmm.
use this to train one of your molecular property predictors, and let's just see if this works.
Right.
Um,
Right.
and then our once we had our first model trained up and we ran our first set of predictions and validated our first handful of predictions, we were observing that this could actually work, right? And this model or this model architecture wasn't necessarily limited to physical chemical property prediction, that it could also be applied to, more complicated and messier
Hmm.
biological data sets as well.
Yeah.
And then that's how I really began to appreciate the utility of, algorithmic approaches to antibiotic discovery in general, right? And now my lab is, you know expanding on a lot of these approaches, um, both in terms of the types of molecules that we're discovering, as well as the phylogenetic diversity of species against which we're looking for molecules as well.
Either from your own personal experience or working with new students and postdocs in your group, or people you've worked with in the past who are interested in getting started with machine learning, like how do you recommend that they start out?
Yeah, if you're coming from a biological or biochemical background like I did, um, it's the first few months is challenging, and the 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 piece of advice that I always give is, you're not going to understand the words that are ever being said, right?
Hmm.
And but that I feel like that's anybody trying to do cross-disciplinary research, right? So the activation energy in order to get comfortable in a new field is super super high, and the
Yeah.
probability of quitting is really really high at the start.
Uh-huh.
Um, but it's one of those things, like you just have to, if you are interested in applying a
Hmm.
certain, skill set to a new problem, right?
Hmm.
You just have to be comfortable being uncomfortable for a few months. But it will
Right.
come, right? It's like you have to read the papers, talk to the right people, talk to people
Yeah.
who are like bona fide experts,
Uh-huh.
and then just like kindly ask them to help you along, right? And you'll
Right.
you'll get there. I mean, I'm not uniquely talented or clever, right?
Hmm.
So, um, but I genuinely felt at the time that the application of these, contemporary deep learning approaches could meaningfully
Right.
change how we discover drugs, right?
Uh-huh. Uh-huh.
So from my perspective, it was a worthwhile investment of time and energy to try to get, comfortable with this new field.
Do you have like specific resources or uh, things that you recommend people do in terms of like pulling code off of GitHub or looking at particular papers or their videos that you like watching? Like, is there anything you would recommend?
Oh, I mean, like the internet is just the greatest resource of ML stuff ever, right? So like I still do. I mean, I'll have some, random ML question stuff that's like at the fringes of my knowledge, and then you
Uh-huh.
just, go onto the internet, type it into Google, and you'll find an answer, whether it'll be on like a blog or
Right.
whatever. But like there are just so many like endless resources online to
Yeah.
to and like to facilitate, you know, learning of all of these complex concepts for folks who are non-experts, right? Um, like yeah, it's just yeah, YouTube videos, Google it, like it's all there. Like you just have to be like willing to kind of again, it's like you're going to be uncomfortable for the first little while, at least, especially coming from like from my perspective. Like I'm a biochemist
Uh-huh.
trying to do computer science stuff, and that was super hard at the start because I didn't know anything, right?
Yeah. Uh-huh. Uh-huh.
So it was lots of like, real basic tutorial type videos, and then over
Right.
time you get, you know, more well versed in the field. It's just like learning anything, right? And then now it's like you can pick up an ML paper and be kind of okay with it. I'm not an expert. I would never claim to be a machine learning expert.
Uh-huh.
That would be a lie. But at least
Yeah.
I can have a conversation, right? And I feel like that's half the battle, right? Like at least I know enough to have a half intelligent conversation with a true machine learning expert in order to build collaborations that, encourage development in the field that I'm interested in, which is antibiotic development, right?
Right. Right. Yeah, yeah, and that's part of why I was interested in chatting with you because people that I'm talking with have taken pretty diverse approaches from really just sort of diving in headfirst and trying to become experts themselves versus like working with collaborators and bringing their own scientific expertise to the problems at hand.
Yeah, and you got to think. I mean, like every biological field, right? Whether it's or synthetic biology, whatever. Like everything's getting like so complicated, and the edges of all these fields are becoming blurred anyway. In order to make, truly, groundbreaking discoveries, right? Really important stuff. You have to be comfortable in multiple languages, right? Because that's where all of the exciting science happens, in my opinion,
Yeah.
right?
So based on your experience, because you did some like training set development and might have a unique perspective on this, are there types of projects that just aren't a good fit for machine learning? Like, so for, if people are curious, like they have a research project and they're curious about whether it would benefit from the use of machine learning. Do you have advice on like what key ingredients need to be in place to be successful?
Yeah, so the obvious one is you need to be able to access like reasonable quantities of very well controlled training data, right?
Yeah,
Um, and and reasonable quantities, that's a very loose. I specifically use that term because every every machine learning algorithm and every prediction task is going to require a different amount of data, and sometimes you'll be able to get away with a little bit smaller data set, but sometimes you're going to need tons. And again, smaller and tons is all relative, right?
right.
You have to gather the data set that you have, try to do something, and then you'll know right away whether you have enough training data or whether you don't, right? But
Uh-huh,
that's all
uh-huh.
empirical. Like there's no like a priori like gold standard mechanism to know whether you have enough. So that's the first
Yeah,
thing. Um, and the particular emphasis there should be on quality too, because if you
yeah,
have a huge quantity of poorly defined, poorly controlled data, you don't know what your model is going to learn, right?
yeah.
And you'll think your model is learning one thing right? Let's say I want to predict whether a molecule has anti-cancer activity. And then you
Mhm.
scour the internet and you pull together a million molecules from a bunch of different screens. Well, that's not controlled. Those data were gathered using different experimental methods. What is your model actually learning at that point? You have no control, right?
Uh-huh.
So when you take this model that in silico has really great performance metrics, all this stuff, and then you take that model and then run predictions for anti-cancer activity, and you test those molecules and none of them work, well, it's
Mhm.
because your model probably learned some, inherent structure in your training data that you didn't
Uh-huh.
perceive and is not reflective of what you're trying to do. Right?
Right. Uh-huh.
Which is
Uh-huh.
why I'm a huge proponent of, well, if I have a wet lab or I have a collaborator with a wet lab, we should gather our own training data to make sure that we know what our model is learning. Right?
Mhm. Mhm.
That's the first one. The second one, and this, I mean, this is as true in machine learning as it is in like any, scientific endeavor, is if you don't need to do something super complicated, i.e. a contemporary deep learning approach, don't do it, right? If there's a
Uh-huh.
simple mechanism that gets you an answer that is
Mhm.
useful to you, just do that.
Mhm.
Why would you burden yourself with trying to make something like way more complicated than it needs to be, right?
Uh-huh.
Like science is complicated enough. So like why are we like there's no point to add complexity for the sake of adding complexity. If a simpler
Mhm.
computational method, you know, some
Uh-huh.
some some classical machine learning approach as opposed to some contemporary neural network, let's say, will
Right.
get you the
Uh-huh.
same answer. If they converge on the same answer, you don't need the neural network. Don't use it,
Mhm.
right?
Right. Uh-huh.
Um,
Yeah, that's interesting. That's actually been one theme of people I've talked to so far, is like either comparing their results to sort of simpler models and then deciding that's not sufficient, and you want to increase in complexity, or just appreciating that that really complex models come with their own burdens associated with them, and you can learn a lot less from them in some cases. And
Stop trying to chase perfection. You just need something that works good enough for what you're trying to do, right?
right, right,
So just like
hmm
do that in the simplest way. At least that's my
yeah,
perspective, right? But I don't know, I'm wrong a lot. but but that to me that just feels right, you know?
yeah. hmm
So that's one
Um,
that's like a two things that I caution people. If you can keep it simple and make sure you understand everything about your training data.
right, what's going
And,
in? Yeah.
yeah, and then everything will kind of sort itself out after that. At least that's my
Mhm.
experience.